Okay, so last time we talked about maximum range, and we went through the problem quickly in the lecture. There's a worked example if you go to the website on an inclined plane, which is a little bit harder than what we did in the lectures, and there you have to resolve the acceleration due to gravity parallel and perpendicular to the plane. So that, I mean, a projectile on an inclined plane is as hard as it will get, right? That's probably the hardest kinematics question without involving calculus that you'll be expected to be able to do. Okay, so next topic is uniform circular motion. So when we mean uniform, what we mean is that we've got an object, obviously it's circular motion, so we've got an object going round in a circle. Uniform means that it's going round with a constant speed. You obviously can't go round in a circle with a constant velocity because velocity is a vector, and if you don't change your direction, you aren't going to be going round in a circle, right? So you can't go round in a circle with a constant velocity, but you can go round in a circle with a constant speed. So the magnitude of the velocity remains constant. So just a little bit of vocabulary. The time taken for one revolution is what we call the period of the motion. And this actually applies for any repetitive motion. So for circular motion, one period is the time it takes to go around one circle. Next term, if you do physics 146, you'll do vibrations. And then the period of the vibration is the time it takes for the object to go through one whole cycle of the motion. So that's the definition of period. And since we've got a circle, a circular motion, we can relate the speed of the object to the period of the motion. If we've got an object here and it's going round in a circle and back to where it started, so it takes a time taken for one rotation is equal to t, which is the period. And if you've got a circle radius r, the distance traveled, remember now we're talking distance, not displacement. Distance is just the circumference, so that's 2 pi r. So the speed, which is the distance traveled divided by the time, not the velocity, right? If we're doing average velocity, it would be the displacement divided by the time. But here we want to calculate the speed. Then the speed, which is the magnitude of the velocity, is equal to the distance traveled, 2 pi r over t, right? So that's the relationship between the speed of the object and the period of the motion, t, right? And of course, you can rearrange that to calculate the period of the motion in terms of the speed, where here r is the radius of the circle. Okay, so that's how we calculate and relate the velocity, the speed, sorry, and the time it takes for one revolution. Okay, so we've got circular motion. So we know that the velocity is changing because the direction of the velocity vector is not remaining constant. And any time we have a change in a velocity, we have to have an acceleration. So now what we want to do is we want to calculate what is the acceleration for an object that's moving around in a circle with a constant speed. So if we go back to our object here, and we're going to consider it moving between 2 points. So here is its circular trajectory. Oops, not very well drawn. And these are the 2 points it's moving between, right? And if this is the center that it's rotating about, then we've got 2 lines out here, which are the radii, and these are both forming right angles with the trajectory, right? Because a radius is always perpendicular to the circle. So if we're considering a small period of time, then this will only be a small angle, and so we'll call that small angle delta theta. And so we've got the object here at point A moving to point B. And this is going to happen in a time, and of course it's a small time because it's a small angle, so we'll call it delta t. So if we look at the velocity at point A, the vector has to be a tangent to the circle. So not very well drawn here, I'm afraid, but I'm a physicist, not an artist. So we've got two velocity vectors here. So we've got the velocity at A, and we've got the velocity at B. Now, these velocity vectors here are tangents to the circle, right? Because it's the direction the object's moving. So this is going to be a tangent to the circle here and a tangent to the circle here. And so this means that this velocity vector is at right angles to this radius, and this velocity vector is at right angles to this radius. And since these two radii have an angle delta theta between them, these two velocity vectors are also going to have an angle delta theta between them. So I can draw this bigger to try and make it clearer. I can draw it like this, where this is velocity B, and this is velocity vector A. And this angle here is delta theta. So what I'm going to do now is I'm going to split this isosceles triangle up, because remember we're talking uniform motion. So the magnitude of A is equal to the magnitude of B, and we get that from uniform circular motion, right? So given this condition here, these two are going to be equal, so I can split this up. If I call the length of this V, right, because the length of each of those two vectors is constant, and we'll just call that V, the magnitude of the velocity, then I can split this up down the middle here to end up with a triangle that looks like this, where the length of this side is V, this angle here is a half delta theta, and if I look at this, the bottom of this triangle here, remember I start with a velocity A, I end up with a velocity VB, and so this here is my change in velocity, right? So I start with this velocity, I end up with this velocity, so I just take what I have to add to this velocity to get this one is just this vector here, and so that's my change in velocity delta V. So the length of this side here is a half the magnitude of delta V. All I'm caring about in this diagram are magnitudes. I'm not worrying about directions now. This diagram was had the directions in to show you how they were related. This diagram now, I just care about the lengths of the sides. So if I look at this, then I can use a trigonometry. So the sine of this angle is equal to the opposite side, which is a half delta V, and I'll write it without the arrow, so that's shorthand for meaning magnitude. So it's a half delta V divided by the hypotenuse, which is V. So a half delta V is equal to V sine a half delta theta. Okay, so now we have to do a little bit of an approximation. Since I'm talking about small times and small angles, right, this quantity here, which I'm taking the sine of, is going to be small. And I can, in fact, make it arbitrarily small. I can just shrink the time period I'm considering and make it smaller and smaller and smaller. And for very small angles, what you find is that the sine of A is roughly equal to A. Now, you probably won't do this in maths until, I think it's the winter term in Maths 114 when you're doing calculus for trig functions, and then you can express this as a power series, and you'll see that that's the case for small values of A. But for now, you'll just have to take my word. If you don't believe me, you can get your calculator out, switch it to radians mode, not degrees. But if you put this in radians mode, which are the natural units for angle, and put in very, very small numbers and take the sine of it, then you will find that you will get something that's almost identical. And the smaller you go, the more accurately the sine is equal to the angle in radians. So this is, and in the limiting case where the angle goes to 0, this in fact becomes perfect because the sine of 0 is 0, right? So I'm going to make an approximation here, and I'm going to say that this is roughly equal to a half delta theta. Right? So in this case now, I get a half delta V is equal to V times a half delta theta. So I can cancel the halves, and this gives me a relationship, delta V is equal to V delta theta. Okay, so that's half the thing done. So now I'm going to go back to this diagram here, and what we want to do is we want to consider the distance here. So distance that it's been moved. Now, if you remember your geometric formulae, the length of the arc of a circle is just the radius of the circle multiplied by the angle it subtends in the center in radians, right? So the distance moved, we'll call that delta x, is equal to r times delta theta, right? So that's our change the distance moved. It becomes a displacement in the limiting case that delta theta becomes small, because when delta theta becomes small, this starts to look like a straight line. And in the limit that delta theta tends to 0, this does actually become a straight line, right? So again, we're using our limiting, the idea of limits from calculus. So I've got a distance, and I've got a relationship here. So next thing I want to do is, since we're wanting to calculate the acceleration, I better write down what the acceleration is. Well, our acceleration, of course I'm doing it in magnitudes now, so all I'm calculating is the magnitude of the acceleration, is equal to the magnitude of the change in velocity divided by the time delta t, right? And then I want to take the limit as delta t goes to 0. Right? That gives me the acceleration. So this is equal to the limit of delta t going to 0 of, well, what have I got here? I've got delta v is equal to v delta theta. Right? So that's my delta v. And I've got delta t here on the bottom. Well, delta theta, if I rewrite this formula here, I can rewrite delta theta is equal to delta x divided by r. And so I've got the limit as delta t goes to 0. If I substitute this into here, I'm going to end up with v over r times delta x, over delta t. Well, the limit as delta t goes to 0 of delta x over delta t is v, right? I'm going to end up with the velocity. So what I end up with here is that the magnitude of the acceleration is just v squared over r, because this quantity goes to v. All right? So what I've shown here is that the acceleration for an object moving in a circle is, the magnitude of the acceleration for an object moving in a circle is simply v squared divided by r. Right? Now, the next question you want to ask is, well, what is the direction of that acceleration? Well, if we go back to this diagram here, right, we can see that as delta theta tends towards 0, right, this is going to as that angle tends towards 0, these angles here are going to tend towards 90 degrees. So in the limiting case, where delta theta goes to 0, this angle here will be 90 degrees. So the acceleration will always be at 90 degrees to the velocity. And as you can see here, it's pointing in this direction, so the acceleration vector will point inwards, right? It points inwards towards the center. And the magnitude is given by v squared over r. Okay, any questions on that? Good. Okay, so we've calculated the acceleration. And this is all just explaining what I was saying. So, but the last part here is that, so what happens is as the speed increases, the acceleration increases. So if you've got a constant circle radius and you start to increase the speed that you're going round, then your acceleration also increases. Similarly, if you decrease the radius, so if you go in a smaller circle with a smaller radius, your acceleration also increases. But it depends on the square of the speed, and it's inversely proportional to the radius, right? So that's how the acceleration changes as you change your speed and radius of the circle. Okay, so first clicker question. Is the acceleration of an object undergoing circular motion at a fixed speed constant? So yes, no, or it depends. I haven't given you enough information. Stop. Okay, let's see what the vote. Wow, okay. So except for the guys who went for D and E, we've got a roughly equal split almost between A and B, with a couple of you going for C. Okay, so turn to your neighbor and try and convince them that you got the right answer. Okay, let's vote again and see if anybody's changed their mind. Okay, let's stop. Oh, okay. So we have a slight imbalance now. I'll show you the correct answer and then tell you why. No, it's not that. There we go. B is the right answer. So why is B the right answer? Well, if I can get the paper out. So we've got our object going round in a circle, right? So here's our object merrily going around. So when we're at this point here, what direction is the acceleration? Right? Into the center, yeah? So when we're here on our circle, that's not quite circular, the direction of the acceleration is always also in towards the center. Right? Now, acceleration is a vector. So what that means is we have a magnitude plus direction. Now this is constant, right? This, not constant. So the acceleration is not constant, right? Because only its magnitude remains the same, its direction changes. And if you want to think about that, I mean, the other way you can think about it is that if you were writing this down in 2 dimensions, if you split it up into components, you'd have an x component and a y component. And clearly the x component would be negative at this point because it would be pointing in this direction. And it would be 0 at this point because there is no x component of acceleration. So if you just looked at one of the components of acceleration, it's very easy to see that that will change as it goes round in the circle, whereas the, and it's the same for the y component. Yes, if you add them together to get the magnitude of the vector, that will remain constant, but the individual components are changing all the time, and so therefore the acceleration is not constant, only the magnitude of the acceleration is constant. So again, you always got to be careful about think about whether you're talking about a magnitude or a scalar or a vector quantity. And with a vector quantity, it's not just the magnitude you have to worry about, it's the direction as well. Okay, so circular motion is how science fiction authors have come up with a way of giving us gravity in space. And the reason this is important is because if you go into sort of low Earth orbit, which incidentally has gravity, as we'll see in the next section of the course. Gravity, when they say, oh, you're weightless in space, actually that's wrong. It's called apparent weightlessness, and it's the same sort of weightlessness you get if you were in an elevator at the top of a tall building and the cables suddenly broke, and as you were plunging to your death, you would have a few seconds of weightlessness to enjoy. Although enjoy might be a bit of a strong word there. But it would be exactly the same weightlessness that the astronauts have, and obviously, in that case, both of you have a weight, which is why you're plunging to your death in the elevator. With the astronauts, they've mastered the trick, I think it was as Douglas Adams said, of throwing themselves at the ground but missing, because they have such a large sideways velocity that by the time that they end up going round in a circle, although they're falling, of course, always to the Earth, and that's in fact how you can tell that they have a weight, is because they are going round in orbit. And if you have true weightlessness, you do not accelerate in a circle because there is no force acting on you, and there's therefore no acceleration. But we'll deal with that in the next section of the lectures. So the way these artificial gravity works is that you live on the side of some rotating space station. So here's it's the Babylon 5 one, and this is the 2001 Space Odyssey. So you live on the inside of a rotating space station, and you move with some velocity around, some speed round in a circle, and that of course then means that you have an acceleration, and you can calculate the magnitude of that acceleration, and if the magnitude of that acceleration is equal to the magnitude of gravity on the Earth's surface, it feels like you've got an acceleration due to gravity, right? Remember, here on the Earth's surface, everything accelerates downwards at a uniform rate, so if you were standing on the inside of a space station, moving around with a particular speed, everything around you would accelerate with the same, at the same rate. So what you've got is you've got the inside of a space station here with somebody, this is not to scale, standing there, and they're rotating about some axis here, radius r, and so what you want is if the floor of the space station is moving with the speed v, you want the acceleration at the floor of the space station, the magnitude of the acceleration, to be equal to 9.81 meters per second squared. So we start with our relationship that we just calculated. A is equal to v squared over r. We're given the dimensions of the space station, so we're told it's got a radius of 750 meters. So we can rearrange this, and we'll get and so therefore v squared is equal to 9.81 times 750. And if you stick these numbers into the calculator, you end up with 85.8 meters per second to the -1. Now, the reason we don't have space stations is because in order to be able to generate this velocity itself in space is not a problem, right? There's no air resistance, not hard. But the problem you've got is twofold. First of all, you have to build something that's strong enough to hold itself together spinning round at speed like that, which is one problem, right? So that needs a lot of material, and it's expensive to launch weighty things into orbit. But the other problem is that you do actually have to have a large radius. Of course, you could make this 10 times smaller. If you make this 10 times smaller, this goes down by a factor of 3 and a bit, which looks good because then it's not moving as fast, and you might think that's easier. But the problem is that if you notice here, the acceleration is inversely proportional to the radius. So unlike, on the Earth's surface, the gravitational field between the floor of this lecture theatre and the top of the lecture theatre is very, very slightly different. It's so such a tiny difference in gravitational field that we don't notice it, right? It's a very, very small effect. In fact, even by the time you've gone up as far as orbit, the effect on your weight is considerably less than 10%. So it's a very, very small difference. But if you made, say, a space station that was 10 meters in radius, right, then, or even more, if you did one that was sort of 2 meters in radius, then your feet would be feeling the full force of gravity and your head would be weightless, and you'd probably get highly disoriented, right, because you'd be feeling different gravitational fields over your body, and that would not be fun. Right, so that's part of the reason it's building a structure that's strong enough to withstand the pressure, but also the fact you have to build a large one so that it has a big radius, so that you don't end up with astronauts developing interesting forms of motion sickness. Okay, so supposing someone is standing on the inside surface of the station, what direction are they accelerating? Are they accelerating upwards towards the axis, downwards away from the axis, in the direction of rotation, opposite to the direction of rotation, or are they not accelerating at all? So, okay. So, turn to your neighbor and try and convince them that you've got the right answer, because we have a nice spread there. We'll vote again, see if anybody's changed their minds. Okay, so let's see what we got. Okay, so now we have a clear winner. Not only do we have a clear winner, we have a correct winner as well. If this thing will ever display it. Okay, so A there is indeed the right answer. So why is that the right answer? Well, you've got this person who's standing on the bottom of the station like this and moving round with some speed v, and they're going round in a circle. So therefore, they have an acceleration towards the center, right? Because we've just shown that anything going round in a circle is accelerating towards the center. Now, the reason that if, say, they were holding something and they let go of it, it would, of course, fall to the ground. So if they had a ball here and they let go of it, what they would see is they would see the ball drop to the ground. And so they may conclude that, oh, the ball is accelerating downwards, therefore everything accelerates downwards and out, which is, I think, why a lot of you, or a fair number of you, picked B. But that's not actually what's going on. What's happening is the entire space station and environment is actually accelerating upwards to meet the ball. If you think about this ball here, when they let go of it, if you're in outer space, a long, long way away from any gravitational mass, there's no gravitational field, nothing, right? There's no force acting on the ball. You let go of the ball, there's nothing causing it to accelerate, right? We'll deal more with sort of forces and things later, but you let go of the ball and nothing will happen to the ball. It will just stay there, right? What will happen, though, so what will happen is that the space station will accelerate round, because this ball, when you release it, has got some speed moving, will have a constant velocity here. It's not accelerating, it's moving with a constant velocity. So it will move in a constant velocity like that in a straight line. But of course, you standing on the space station come round here with the speed of the space station, and what you see is you see the ball looks like it moves towards the ground, but it's not. The ball is actually moving in a straight line. You are moving round and accelerating up towards the ball, and that's why it appears to accelerate downwards. It's not accelerating downwards. It's not accelerating at all, in fact. It's you that is accelerating up to meet it. And But this effect here, where if you're moving around in a circle, in fact, if you're on a fairground ride that goes round and round in a circle, if you're holding something out, it's hard to make you to move your hands in towards the center. And so it feels to you almost as if there is some force pushing you away from the center. And that we'll deal with when we get to forces, is called the centrifugal force. But that force actually doesn't exist. It's what we call a fictitious force. It's a figment of your imagination, simply because you are actually accelerating towards the center, and so therefore it's actually a force that's the only force that's real is what's called a centripetal force that pushes you towards the center. But we'll deal with that more in forces. But for this one, you do accelerate towards the center, because anything moving in a circle does, and the ball, if you drop it, moves in a straight line, and you accelerate up to meet the ball, not the other way round. And so therefore you are always accelerating towards the axis, even though you might be fooled into thinking that you're not. Okay, so any questions about that? Good, okay. So, I covered that bit. So what this does now is we can define something called a reference frame. And the reference frame is how an observer sees the universe. So, it's you measure everything that you see relative to yourself, right? So if, for example, if you're on a car driving down the QE2 highway to Calgary, and you pull out to overtake a lorry or a truck, as you look out the window, it might appear that the truck is moving backwards, right? Whereas, of course, if you had somebody standing at the side of the road looking at your car and the truck going down it, they'd see the truck whiz by at 120 kilometers per hour, and you going faster past them. Actually, not 100. Yeah, you're not supposed to go that fast. But anyway, yeah, sorry, I get Europe. It's 120 here, 110. So the observer on the side of the road stationary would see the lorry zip by, whereas you in the car would see the truck slowly moving backwards, right? And that's because you're in a different frame of reference to the observer standing at the side of the road. So we define these frame of reference as how the world looks according to an observer. So what we have to do, if we're going to do that, is you can then ask, well, what is the velocity of an object as seen by a particular observer looking at it and measuring it? And there are two types when this becomes useful. There are two sort of times when this can become useful. Boats and planes move through a medium. So boats, they sail through the sea, planes fly through the air, and they have a speed relative to their medium, right? So planes have a speed relative to the air around them, and that's what's important for them generating lift through the Bernoulli effect on their wings, right? It's the speed relative to the air around them. And in fact, this is why, if you've ever been on a transatlantic flight, or even east and west in Canada, if you're flying to Toronto, going from here to Toronto, it's about 20 minutes shorter flying time than heading from Toronto back to Edmonton. And that's because in the upper atmosphere, there's a jet stream that blows from the west to the east. And so when you're flying towards Toronto or onto Europe, you are going with the airstream at a constant velocity relative to the air. And when you're flying back, you're flying against it, but at a constant velocity relative to the air. And of course, what matters for the length of your trip is how fast you're moving relative to the ground, not relative to the air. So if you're moving with the airstream, you move faster relative to the ground, and if you move against the airstream, you move slower relative to the ground, right? So that's where you have to either add or subtract the velocity of the air, and the same thing goes for boats. Another time it's useful is if you're calculating collision courses. So if you're wanting one object to hit another object, then one way of doing this is to calculate the velocity of that object relative to the target and make sure that the velocity is heading straight in towards the target and not going to miss it one way or the other, right? So it's useful for calculating collision courses. So the way we do this is we've got to transform between one reference frame and another reference frame. And in Newtonian physics, this transformation is called a Galilean transform after Galileo. And since in Newtonian physics, time and space are the same for everybody, this makes our transform rather simple. Now, you may think, well, that's a pretty obvious statement, but wait until we get to relativity. It gets fun then. So, you know, we do actually have to worry about that in relativity, and we have something called a Lorentz transform. But for Newtonian mechanics, Galilean transform's good. The requirement is that all the laws of physics in all non-accelerating reference frames are the same. So if an object's not accelerating in one non-accelerating reference frame, it had better be not accelerating in any other reference frame, right? We don't want it to be accelerating in one frame and not accelerating in another. And so what we come up with is this the Galilean transform to transform velocities from one observer's point of view to another observer's point of view. And I won't go through the maths, but simply if you're wanting to transform a velocity here that's measured in this frame, S, and you've got an observer who's moving with a velocity v relative to s. So imagine this person, for example, is on a train, right? Then the velocity u prime that the observer on the train will see is going to be this velocity here minus their velocity relative to if this was the platform, say, right? So if you've got a ball rolling along the platform with a velocity u, and a train moving through the station with a velocity v, then the velocity that the person on the train will observe for the ball is this speed minus the speed of the train relative to the platform, right? And so written another way, the velocity on the platform is the velocity that the passenger on the train will observe plus the speed of the train, right? So if they see, for example, they see the ball as stationary out of their window, they don't see it moving at all, what that means is somebody on the platform would see the ball rolling at the same speed as the train, right? But the key point to note here is that these are velocities, so you have to worry about directions, right? So it's not, when you're doing the subtraction or the addition, you've got to remember about additions because there's no guarantee that these guys are going to be parallel, right? And in fact, there's a question on the assignment towards the end about a cyclist approaching a train where you have to worry about this. So be careful to take into account directions. Okay, so the last example here, because we're running behind time, we should already be on Newton's laws. I actually covered in the worked examples on the website. So it's the last question on the kinematics worked examples, and it's a problem about two boats, one that goes downstream and comes back, the other goes across the stream and comes back, and you calculate the time difference between them. Please look at this on the website and make sure you understand how to calculate the relative velocities, not only because this is an example of the sort of question you'll have on the assignment and possibly on exams, but also because this example, when we get to relativity, is very relevant to the background of relativity, where instead of using boats, they used beams of light and had the relative motion of the Earth, and came up with one of the most famous negative experiments in the history of physics. So I've got 5 minutes left, so please don't go now, because I want to get on to Newton's laws, because we are behind, we are quite a way behind. So please read the worked examples for kinematics. So the next part of the course is on Newton's laws of motion and dynamics of particles. So now we're not just going to be studying the motion, we're going to be asking what's causing the motion and what rules do we have to calculate how, what sort of motion will be caused by objects out in the universe. So the first person who studied this was a guy I'm sure you've heard of, Isaac Newton, who came up with 3 laws of motion. So the first law is usually often understated and people don't worry about it too much because it simply says a body will remain at rest or in motion with a constant velocity unless acted upon by a net external force. So, it seems almost like this is a subset of Newton's second law when we get to that. However, it's actually a very useful and very fundamental law because it tells us something about the universe. And what it tells us is that we talked about inertial reference frames that weren't accelerating, and this law tells us that we can define that, right? When we're doing Galilean transforms and we're subtracting velocities, right, the question then arises, well, how do we know when someone's at rest, right? Because it might be just that everything around them is moving with the same velocity that they are. How can we be sure that they're not moving, right? And you can't, in fact. However, we can be certain that they're not accelerating because all they have to do is they just take an object and they put it on a table, or they make sure it's not acted upon by any external force. They put it in a situation where there's no net external force, and they look at it and does it accelerate? And if it doesn't accelerate, they know then that they're in an inertial reference frame because Newton's first law holds. So it's a very useful law in terms of defining a non-accelerating reference frame. Sometimes, if it's the first time you've encountered this, which it shouldn't be, but usually school kids, the first time they see this, think it's a bit counterintuitive because, well, if you stop pushing something, it stops moving. And that's, of course, just because you've got a frictional force that slows it down and stops it. Okay, so well, we've got time for one clicker question. So if we've got a car turning a corner, maintaining a constant speed of 30 kilometers per hour, do we have a net external force acting? Okay, good, right? So we do have a net external force because you're going round in a corner. It's half a circle. You must have an acceleration towards the center. If you have an acceleration, you've got an external force acting, and so B is the correct answer. Okay, well, we'll stop there then, since you're all going, and we'll skip a few questions next time.